All right, I think we're ready to get started with our next keynote. If you could take a seat, that would be great. It's my pleasure to introduce our next speaker, Dr. Dennis Gannon. He has more than 200 refereed articles and 3 co-edited books. He got his PhD in computer science from the University of Illinois, Urbana-Champaign, and a PhD in mathematics from the UC Davis School. So 2 PhDs, not just one, right? He's a professor emeritus in the School of Informatics and Computing at Indiana University. And from 2008 to 2014, he was with Microsoft Research. Most recently, he was director of the Cloud Research Strategy. In his role, he helped provide access to Azure Cloud computing resources to many of us and over 300 projects in research and the education and community across the world. I had the pleasure of being on a panel with him yesterday, and I learned a great deal, and I'm really looking forward to today's discussion, so I'll turn it over to Dr. Gannon.
Thank you very much. So it's a pleasure to be here, and I want to thank the organizers for inviting me. I get to tell my wife that I finally got a live performance in a theater on Broadway. That's very exciting. Also noticed that in the program, my talk is mentioned twice. Each one had a different strange title. And I decided, actually, both titles were awful. And so here's the real title of the talk. And this is what I'm really going to be focusing on is how do you program the cloud? Because I've spent, the last 6 years doing that and working with the academic community on trying to figure out how do we put stuff in the cloud? How do we make programs in the cloud? So, but first I'll give a little tiny cloud history, and then I'll talk about some of the challenges for science researchers. And I'm going to go sort of dive into the software stack. I'll talk about software-defined networks and other software-defined things, and the container revolution and microservices. And then I'll talk about managing clusters of services and some conclusions. And it's interesting, the last two keynotes, yesterday and today, really gave away a lot of the things that I'm going to say. So I hope this isn't too boring. But anyway, it really does reflect everything I've learned in the last few years. So first of all, a little very tiny bit of cloud history. And that originally the data centers, when I first went to Microsoft, they weren't talking about clouds, they were talking about data centers and the internet properties, as they were called. And these are things like the online portals, email, MSN, all of the big, what you call internet companies had these very large services that they ran for people, and you know all of these things. And these services required that they build very large data centers. And these are very big, expensive things. And in particular, they range in price for a single data center between $500 million and $1 billion. That's a lot. But in order to compete with each other, they have to make those data centers incredibly efficient and smart. And by smart, I mean they had to really understand the big data analytics because of their customers in order to better please their customers. And they had to deploy this stuff at scale. And what this did is this led to several really significant revolutions, I think, that we've seen in this cloud community for the last 3 or 4 years. First of all, the whole public infrastructure services and platform services. This has just really come about relatively recently, and it's a revolution, as well as the way we architect data centers. That's been a revolutionary changes there, in that we've seen the emergence of a cloud software stack that I'll talk about. And, reflecting the talk that we just heard earlier this morning, machine learning. That has been enormous. But all of these revolutions has also served to generate a collection of really fascinating, innovative startup companies that are really changing everything. They're helping to define the software stack as well as the application stack regarding machine learning. So getting into the machine learning just a little bit, and we heard quite a bit about it in the last talk, is there's been a number there's really been a revolutionary change. I know inside Microsoft there are many thousands of people just working on machine learning. Same is true with Google and everybody else, IBM we certainly know. And some of this has made have had a profound impact. Take natural language translation. There's the translator from Google. Skype has a voice-to-voice translator. And this stuff really came to be with the advent of a collection of massive amounts of translated text and doing statistical analysis on this text. And the amazing thing about some of this analysis is that as you work on the translation, say, from French to German, the translators simultaneously get better in, things like Spanish to Portuguese. They learn and they generalize themselves. One of the people at Google at a talk I heard, basically, he said, now we can translate from Farsi to Klingon without knowing either language, which is, I think, probably true. So the other thing that we've learned and we've seen is deep learning, these deep neural networks, which started work in the area of really massive scale, multi-level neural networks for image analysis. And this is incredible stuff. Now, we've all seen this. We see our images tagged, on our data collections. Take photographs and you see automatically tagged pictures of you and your friends because they could recognize faces. You could recognize animals. This is a picture from Google on the right, and you can see that different points in the network really represent kind of abstract representations of the things that that node of the network is tuned to see. And these were not trained to do this. These are self-taught, in a sense. There's a node that sort of represents a face. This came from YouTube images. And, of course, with YouTube, you see lots of cats. And so there was an abstract representation of a cat face. Another thing is in the bioinformatics area. In bioinformatics, a lot of genome-wide association studies, and David Heckerman and Microsoft use vast amounts of cloud resources to do a lot of analysis of genomic variations, of looking at many common diseases, trying to understand this in these GWISE studies. But what about the rest of science? Well, it turns out we all have, most of us are academics here, we all have colleagues in the other sciences that are changing everything now. Everything is different. The experiments, simulations, archives, literature, all that data is growing so fast that most scientists now are data scientists, and they're dealing with big data. And my actual definition of big data, a very simple definition of big data, if it's too big for your laptop, you've got a big data problem. And it seems to be what drives a lot of people to do some really interesting analytics using cloud and other sources. In fact, the entire nature of research is changing. And Tony Hay at Microsoft sort of coined this term of the fourth paradigm. Actually, it was Jim Gray, Microsoft, that coined the phrase the fourth paradigm of science. And that follows on the first paradigm being experimental science, the second paradigm being theory. Computational science came along to describe, to simulate the things that we couldn't do actual physical experiments on, such as the birth of the universe. And then now we're in the fourth paradigm, which is science that is driven by data discovery in itself, without a theoretical foundation, sort of discovering knowledge in the information. That's the fourth paradigm. Now we see something else happening, and that is urban science. I see real programs beginning. New York City has a large urban science program, so does Chicago, Seattle, where I live, as well as Beijing has a very big program around this. And this is really all about the Internet of Things in the city and how you use the cloud and the Internet of Things to really optimize the life of the city. And that's going to become more and more important. This is a hugely important topic. Now, I want to go through a little example app. There's something actually in my spare time that I do. It's sort of a hobby, is actually working with some machine learning stuff. This is not Watson, by the way. This is well below that. But I started building some stuff. I was interested in document analysis. And so I started looking at all these data streams and data feeds that you could get to take publications, scientific publications. I thought, gee, I'd like to be able to classify those into their sub-disciplines and subdisciplines. And it turns out, yeah, you can do this, and it's something that gets better the more data you have. I have probably about 50,000 documents that I've compiled, and they stream in about 200 a day. And so it is now big data for me. I can't do this on my laptop anymore. And so I've been moving it to the cloud. And I'm going to use this as an example for how I program the cloud, or at least how I am programming the cloud. I'm not done with this project yet, so I can't report any exciting results. But I'll give you the idea of the architecture to explain something else. Now, programming the cloud. Where do you start? Well, we have these techniques and tools for us serious cloud geeks. And these are the things like microservices and stuff that I'll talk about later. But, again, what about everybody else? And I want to emphasize that this is very important. We have something called a long tail of science. I've got this graph, and the horizontal axis is sort of scientific disciplines. The vertical axis is the ability to deal with complex infrastructure like cloud infrastructure. And clearly the high energy of physicists, they can handle anything. Any complicated problem, if you throw 500 physicists at it, they'll solve it. And so they could do it. The astronomers are doing pretty well with the big data as well. Genomics folks, they're coming along, but then there's all the other scientific disciplines that are out there that they're struggling and trying to figure out, how can they deal with their own research data? How do they collaborate? How do they do stuff? And how do we help them as this cloud community? How do we make it better for them? And I'll talk more about that later. But now, to the software stack. This takes me to the software, cloud software evolution. part of the drive towards the economies of public scale. The public cloud, in order to make it work, you needed economies of scale, and especially in order to compete. And so the really a prime driver is to reduce the infrastructure cost to near zero. And once you can do that, your customers can actually afford to live in the cloud. And it's become more cost effective for them to do things in the public cloud than otherwise. And you need to make it programmable. But from looking at the software stack, at the bottom level we have the sort of the basic hardware abstractions and virtualization, and something I call the data center hypervisor, which is part of every public cloud that you don't see, and you don't want to see, believe me, I've seen it. You don't want to go there. But then, above that, we now have software-defined networks, and I'll say why that's important in a minute. Software-defined storage, as well as above the software, these two levels, we now have, as we heard yesterday, containers and distributed cluster operating systems, Docker, Mesosphere, Kubernetes, which is, if you read, on the web, it's spelled K8S. But anyway, Kubernetes. And then above that, we have frameworks, application programming frameworks, big data frameworks like Hadoop and Spark and Yarn, HD Insight, Reef, Twister, Brisk, all these sort of tools that are emerging. And then above that, you have the actual programming tools. So this is the stack that's emerging, and much of the stack is really turning into open source very fast. So in terms of software-defined networks, this has been a revolution inside the big data centers. And the idea is really, we just used to think about things of hooking up racks and top-of-rack switches, and now it is much more sophisticated, subtle, and flexible. By software-defined networks, many of you already know this, so I'll go quickly through this, really redefine the whole network control plane to a set of uniform abstractions and separations of concern. And so the picture on the right is this notion that you can take and define an abstract network, which might go from your on-premise network into the cloud, and you define it as an abstract thing. In fact, there's a programming language for this I'll mention in a minute. That abstract virtual network then can be literally compiled down into a global network interface, and then compiled from there down to network operating system, actually the switches. And it's not really even the switches anymore. A lot of the network stack runs in the servers as opposed to the switches. This is, again, it has totally changed the way the network inside the big data centers. At Microsoft, Albert Greenberg just basically went in, threw out all the switches, threw out all the things like firewall, hardware, all that kind of stuff. He said, get rid of that. You're going to do it all in software-defined networks. Completely changed the architecture and made it more flexible, easy to manage, and made it very, very easy for the customer to actually extend their network right into the cloud. This is really important stuff. Now, the next thing is software-defined storage. This is, in my area, a great topic for research by this community, and I haven't heard that much about it here. But it's not as well defined in terms of the abstraction and separation of concerns as is software-defined networks. But we have a lot of instances of interesting software-defined storage, like S3 from Amazon, and Azure has a storage system, Ceph, the Swift object stores, and a bunch of others. And some of these things they're not that far apart in terms of their abstractions. There are no uniform standards yet. And for the people, I know there are people here interested in sort of open cloud infrastructure, and I think this is a place that's really important. And a lot of this stuff is built with really clever, sophisticated distributed replication and erasure-coded recovery schemes. And this is incredibly important to make things work in the cloud and be amazingly reliable. But often these storage structures have a misfit with our analytics frameworks. So, for example, in fact, I've seen one project that's really interesting out of Berkeley. A graduate student did a PhD thesis and built this thing called Tachyon, which sits above all of these different data structures. It's basically an in-memory storage infrastructure that is ideally suited to support a lot of these application layers. So I don't know what's happened with this, but this is, you might want to, if you're interested in the subject, do a Bing on Tachyon. Okay. And now back to how to build a cloud application. Well, all right, if I'm going to build one, what are my choices? Do I need what do I need? Do I need resilience? Do I need to be able to run reliably 24/7? Do I have to capture streaming data? Or is it sort of a batch mode? Is that sufficient? What sort of scale? Is this a simple interactive experiment where I want to sit down as a scientist and I want to interact with things? Does it need a lot of cores? Does it involve big data? What are the security and privacy concerns, which I'm not going to say anything more about because that's a whole subject, as you know. And what is the user interface? Is there really a phone app component to this application? So these are all really interesting, questions you have to think about. Now, what I want to do first is consider a very simple, interactive, experimental environment. And this is what a lot of scientists really want. They want to be able to do something in the simplest way possible. They want to do it in the cloud because they could get more scale, and their data might be there. So what can they do? The first example I'm going to show you here is something called Azure ML. And this is the Azure Microsoft. Again, this is not intended to be a Microsoft advertisement. I don't work for them anymore. But this is really cool. And you can use it for free. And it gives you a drop and drag interface to build a machine learning application. It's getting better. It's not that good at really big data yet, but it's getting better. And by composing these things, you can explore your data set, you can do all the data cleaning problems, and when you're all done and you've trained a machine learning model, you press a button and it'll generate a service for that model, and a web service with a REST interface, and you can then use that, that's pretty neat. So this is something that the big team at Microsoft has worked on for a long time, and it's go try it, it's free. Now another one, again, this is something that we've already heard something about quite a bit, and I imagine many of you use the containers and Docker, but I see the science community absolutely adores this technology. It's very cool because you could basically, it runs a host on a host. Well, you heard all about it yesterday, and Docker is one of the open source free implementations of this. The Docker.com company. I actually have to be careful. If you look on the web and do a search for Docker.com, you get something about blue jeans and pants and stuff, but it's different. It's really very cool stuff. And since we heard a big discussion about it yesterday, but I'm going to show you an example of my favorite. And if you go into the science community, especially people like astronomers and biologists, the following thing is something they truly love. And it's called the IPython notebook, because there are a lot of Python programmers. Python and R are a lot of the big analysis programming tools that the science community uses. And by science, I include social scientists, everybody. And this is a very neat notebook. If you've ever used Mathematica notebooks, this is like the same thing, but it really is something that is very powerful in a programmable sense. And so now, when I first tried this, I did this about a year and a half ago. I saw this, I got a hold of it. It took me about 3/4 of a day to deploy this on the Azure cloud. Now, admittedly, sometimes it takes longer to do things on the Azure cloud than the Amazon, but still, it was an effort. And a lot of interaction with Stack Overflow. For those of you that do these things, that's where you find out how to really do stuff. And I finally got it running. But now, with Docker, what I could do is basically I can do a one-liner. I could say Docker run, and I give it some port information and a password, and I say IPython SciPy server. Just give it that, and it downloads it, runs it, fires it up, and it's running. It's just astounding. So you can have it up and running in about as long as it takes to download the container from the Docker repository. So it's incredibly powerful and a lot of fun if you haven't done it. So this is again for the people that don't want to really think about how to program complicated, big computer science geeky applications. This is to get your science done soon. Now let's go back to the geeky stuff. Going parallel. There's really two models that you have to think about when you're going parallel. One is bulk synchronous parallel computing. This has been around forever. And the idea is you have in parallel, you do a bunch of computing on data, and then you have a barrier synchronization of some type where data gets exchanged, and then you do some more computing and a barrier synchronization. And so this is like Hadoop is basically this, right? You do a map and then a reduce, and then if it's iterative, you do another map, another reduce. Spark is something that I consider to be far more flexible, and I'll say some more words about that in a minute. But there are other systems. And so this is it's classic parallel computing brought to the cloud. Now, the other choice that you have is what I would call the asynchronous swarm. And this is where microservices come into place. And there you have a bunch of decisions you have to make. Is this a stateful service? Or are the services stateless, the little nodes? I mean, this is a communicating network of perhaps actors, if you know the actor model of computing. So these might be actors. If they're actors, they're probably stateful because actors respond and change their state according to the messages they receive. Or maybe they're stateless. And there's advantages to both. You send messages between these little services, and then you've got, again, more choices you have to make. Do you want to make your messages to be basically simple REST calls? A lot of times that's really simple, it's easy, but it's not terribly fast. There's other things out there like Facebook. Facebook, like many companies, released something they use internally. And as we talked about at the panel the other day, companies now, it's to their advantage if they're not really in the software business, but they need infrastructure and they build it internally. If they can get the community using that infrastructure and improving it, it gets better and they get great employees. And so they released something called Swift RPC, which is a very nice, lightweight remote procedure call mechanism. Then there's things like the AMQP, the Advanced Message Queuing Protocol, I think it's called. And that's basically what a lot of the IoT messages use. I mean, it's very lightweight, simple message transmission, and that's also very good. And there are a lot of good message brokers out there that are very reliable and quite fun to use. So you make these decisions based on your application. The big challenge, of course, is how do you divide up your computation into this swarm? Now, I'll come back to that. How are we doing on time, everybody? Okay, good. It's only 100 more slides, I think. I'm actually racing right along. A little fast, okay. So bulk synchronous, parallel, and Spark. Okay, now, so Spark is based on the notion of something called the resilient distributed data structure. And it's a way of taking a data structure and distributing it across a bunch of servers. And it's resilient because it tries to sort of maintain locality of that data between operations. So you do some work on these distributed data structures in the compute part of the bulk synchronous. And then you do some reduction operators. And they have a strong library of different types of transformations and reductions. And its native programming language is something called Scala, I'm not sure how it's pronounced. But it's very nice. It's a Java derivative that is a very nice interactive language, and actually Spark is written in that language. The other one, again, coming back to good old IPython notebook, it turns out that the Spark folks have provided a really nice Python interface. And to give you an idea of what it's like to use Spark interactively, I've tried to compute this little sum. Actually, it's incorrect. The sum from 1 to n of 1 over I squared, which actually, if you've read your math, it's already pi squared over 6, so you don't have to do any work if you know what it is. But if you didn't know that, here's 4 lines of Python code for how you would compute that in parallel. So it says, I got an array of size of million. I'm going to partition it into 32 pieces. And so data is, I just say SC, which is Spark context, parallelize the array according into 32 partitions. And now I compute the squares, which I have a little lambda expression, which computes 1 over the I squares. And then I do a reduce, and the reduce is simply addition. And that's it. And then if I don't like that answer, I can go back and I can change it. It is interactive to do it this way. And doing interactive parallel computation in the cloud, it's a lot of fun. I highly recommend that you give that a try if you haven't. So that's that. Now, Microservices. Well, again, we had a great talk yesterday about microservices. And so here's the basic problem if you're a programmer. How do I partition a large heterogeneous application, make it secure, maintainable, fault tolerant, and scalable? Okay, and so this is where the microservice idea comes in. And the idea is to, you guys heard this, and many of you already know this, but so I apologize if I'm repeating myself too much. So you have partitioned the application into small, independent service components, and they communicate with some of these simple, lightweight mechanisms, like the RPCs or the message queue stuff or REST. But each one of these each microservice, the idea is it has to be managed and replicated and scaled and upgraded and deployable independent of the rest of the system. That's what we heard about yesterday. And that's really fundamental. And it is really important because this is something that, as you saw yesterday, is what is at the heart of how you maintain a really large service without letting it go down, but how do you upgrade it? And so each one of these simple functions, each microservice, operates in what's called a bounded context, which means it has its own environment, it knows what it needs to do, it does one thing very well. Now, the other thing that you want to be able to do, is you want to be able to reuse existing services, whatever possible. Because once you decompose it, you find out, oh, some of these components, that's well known. I know a really good solution for that. It's already there in the cloud. Use that. So by tearing apart a monolithic application, you discover these pieces that are better than what was in your monolithic piece. And the other thing is that, as we saw again yesterday, the whole concept of DevOps, which is the new engineering model in the internet companies goes by the expression, you built it, you own it, which means the people that designed it, they deploy it, they debug it, they put the new versions, they own the life cycle of that application. And the old model, you had the developers who were going to develop, they hand it off to the people who deploy it, the people who deploy it say, this doesn't work. They say, well, that's our problem, you fix it, and then lots and lots of testing. Microsoft used to have, very large armies of testers. They're going away pretty fast because the people that are developers are now the testers. And this is all really important. This model is used for massive scalable services by Netflix, Google, Microsoft, Spotify, Amazon. I suspect IBM does too, and many other companies, smaller companies, and that I just didn't mention there. So here's for example, Microsoft. I pulled this from a recent talk they gave. This is Microsoft's really changed a lot. This is a picture of the Microsoft Service Fabric as it exists now. And you notice that they have that the Azure Cloud part over here has got Windows and Linux as a first-class citizen. And that some of their Service Fabric unites all this stuff together, all in support of microservices at the top level. And they then also built that to span across private clouds and hosted clouds so that they really care about that because their customers care about that. These microservices inside of Microsoft have been absolutely critical to the deployment of a lot of the big standard infrastructure that you see. And the same with Google. As you heard, this is now the standard practice because it's the only way to do anything reliably at scale. Now, so I'm going to come back to my example. Now, how do I decompose this microservice? Or how do I decompose this into microservices? I've got the service feeds. I have this machine learning classifier, which is definitely not as good as Watson. And I have my data that goes into my cloud archive, and it classifies things. Well, so I sat down and I started tearing this apart and looking at the pieces that were independent in the microservice sense. Well, it turned out it was actually pretty straightforward, and I learned a lot doing this as I was learning about microservices. On the left side, we have these sort of extraction services, and these are services that are doing the mining of the publication indices. That a lot of RSS feeds and these things. In fact, this part is already running, and it's running independently of everything else. So these are independent deployable units that extract and pull the data in. they push stuff into the data archive. Now, again, an example of using something that's already there that's hyper reliable. I could have used any number of things. Amazon S3, and I use the table service within Azure, which is sort of like a NoSQL database, but it's a table mechanism, and it's very reliable, extremely reliable, very scalable, and works great. And so I use that, so these extraction things, pull documents, clean them up, and put them into the table. Then they send out the AMQP messages to an event queue. Now, in my original application, I had my own little flaky event queue, and I realized, whoa, wait a minute. There's really good stuff out there. There it is, RabbitMQ, but also, the cloud platforms, each of the big cloud vendors has a message queue service that's standard. And so I plugged into that, and that is much more reliable, and it works fine. So I use that as a standard component. Now my analysis parts, well, the way I designed the analytics part of this was so in this way, it's sort of kind of Watson-like, I guess, because I take multiple different machine learning algorithms, and I apply them independently to the data. And so that each one makes decisions, and then they sort of do a voting thing. Now, it's nothing like Watson in terms of sophistication, but it's good, and it's very scalable, and I can scale it across multiple machines. Then once I do that, then there's the final sort of classification. Once I've ranked each document, then it goes into the topic indexes, and I've got more topics than that, but just to give you an idea, then it figures out which topic this one belongs to. There's a feedback part of this I haven't shown, which is when you update a topic or send something into a topic, you need to update the learning algorithm that goes with that. But that's a different subject. But anyway, the main point here is that decomposition into the microservices is actually something that was fairly natural to do, and using the different protocols throughout. Some of it's REST, some of it's message queue stuff. It's different protocols for different purposes. Now, how to manage a cluster of microservices. So once you do this, you have to manage it, okay? Because if you've got maybe, in my case, I've only got about 20 instances at any given time of these microservices. How do I manage? Managing 20 communicating services is a pain, right? So, but it turns out there's many solutions. As I said, there's the Microsoft Server Fabric. There is something from the Docker community called Docker Swarm. We heard yesterday about Google Kubernetes. And another one is Mesosphere. Now, I actually went out and, because I could do anything I want to now, I don't have to use Microsoft stuff, I deployed each of these, and I experimented with them. I don't have a quantitative analysis, but I could tell you now what we heard yesterday about Kubernetes, I was very impressed with, because this whole concept of pods is really something that is unique. But in terms of Mesosphere, and I'll explain what that is in a second, that was really interesting. I deployed them all, and the one that for me was the winner was Mesosphere. So what is Mesosphere? It comes from a project originally at Berkeley, Mesos, which is a distributed system kernel. And so it is a distributed system, it's an operating system of distributed systems. And when you bring it up, you have different pieces of it. There's Mesos, which is the kernel, and it brings up master nodes and backup master nodes that run a lot of the services, together with worker nodes. And the worker nodes are what host each of the Docker containers. And there's something called Zookeeper, which is the system that keeps track of what's there and how it's running and whether it's up or not. And there's also a DNS service. Mesos has a discovery service. And all these things work together very well. Now, it looks complicated, but they've got folks at Mesosphere, which is now the commercial company that took on the Berkeley Mesos project, made it so that you can deploy this in 15 minutes and it'll be up and running, even on Microsoft's cloud, which really surprised me. And it is incredibly easy, and it just stays up and it runs beautifully. In fact, you get a lovely little interface. When it comes up, you bring up a web page which has a dashboard that shows you all of how each of your workers are doing. It's load. You You could examine the services. You could, if there's something that you think needs to be scaled because it's only got 2 instances, you go in and into the web page and say, I think it needs 10 instances, and you just rewrite 2 and put 10, and it goes to work, and bang, deploys 10. If some of the instances start to fail, which some of my code they did, and I could actually watch it as things were failing, and it encountered a bug, it would bring up new instances, which would then fail, but it would keep going. And it was very, very impressive. So I highly recommend doing that. All right, so now I'm getting towards the back end of this talk. What have I learned? Well, first of all, that building reliable asynchronous distributed systems is possible. It is something that I used to work very hard in distributed system stuff, but it was extremely difficult to get reliability. The cluster management is now amazing with Mesosphere, Kubernetes, Swarm. All of these different technologies allow you to do this and to manage it very easily. It's all open source stuff, and it works very well. What about the non-computer science scientists? Again, the containerized science apps are just amazing. The science community is gravitating towards this very, very quickly. In particular, there's things like what are called science gateways, which are being run in the cloud and on some of the supercomputing centers. Excuse me. And things like Galaxy. If you're a biologist, you want to use a system called Galaxy, which patches together a lot of the standard stuff. You can just go on to docker.com, and there's a complete set of Galaxy, a complete instance of Galaxy, and you could just pull that instance down and deploy it again in a matter of minutes, and it's up and running. I say deploy it for the first time, but always from Docker, you have to download the whole image to wherever you're running. Thereafter, it's got a copy of that. Bringing up a new copy just takes a couple of seconds, literally. And unless there's an update to the original container, then it'll update it automatically for you, which is a really great thing. Now, what about the scientists that have access to high-performance computing, or just HPC in general? From this morning's talk, we saw that something that's very important, a lot of the machine learning work that's going on now, although much of it started in the current revolution, started in the cloud, and Microsoft and Google and places like that were doing this, Amazon, everybody. They're all learning the scalable big data machine learning stuff, and they were doing it in the cloud, but that stuff really can run a hell of a lot better on HPC systems. And so I would say, okay, there it is, that there's a real challenge that we have. Can we seamlessly start extending our cloud stuff into the supercomputers? Most countries now have national supercomputer facilities that scientists can use, but can we build sort of a software-defined networking bridge between the cloud and the supercomputer so that some of my services, although they appear in the cloud, I can send REST, messages to them and interface to them, they actually execute somewhere on a really big supercomputer? Because supercomputers are really superior to just public clouds in the way they can do computation. And so what I'd like to be able to do is prototype something on a laptop, push it to the cloud, and then eventually see that migrate to big-time power in a supercomputer. And so, for example, the deep neural network stuff that's happening now. I mentioned that Google originally did this on thousands of servers on their data centers. Now, the main work on the deep neural networks is taking place on clusters of machines with very high performance GPUs and FPGAs and other specialized network hardware. It's sort of becoming more and more specialized to get the high performance you need to do the massive scale stuff there. And so that's really important. One thing I haven't talked about, again, something I consider to be very important, is community data collections. And there are a lot of examples of this. There's, genomics, astronomy, geosciences, earth sciences of various types. And I think that, as the cloud community, we need to think about how we can address community data collections and how our cloud architectures can better support them, in particular in terms of sustainability, sharing, and reproducible science. I think this is something that does not get enough attention in our community, and it deserves it. Now, next slide. Hello. Conclusions. Okay, the cloud has really matured and continues to evolve. Massive GPU-enabled servers will be migrating to the cloud. They're already there in some cases. Amazon's already done this years ago. And this container technology is making the application deployments really easy, as well as the orchestration, the management, Kubernetes, Mesosphere, make it really reliable and scalable. The portable data analysis tools are emerging with Scala and Python for Spark and R, and DataDR is another one. But we still need, again, we need ties between the cloud and the supercomputer. We haven't yet completely figured out how to deal with the Internet of Things and community data collections. And now to end, I've got some predictions, okay? They always have to have something like this, and they're not very exciting because I think you guys are already talking about some of this stuff. That the data centers are going to have better supercomputer-like networks. You're going to see more node-level accelerators in the data centers open to people that want to buy computing on the fly from a public cloud. FPGAs in particular are becoming very, very interesting, and their deployment as parts of the resource in a cloud, it's going to come very soon. Okay, so I like Siri and Cortana a lot. They're really good at reminding me that I better get to the airport on time, and that it's, somebody's birthday is coming up, and what I should pick up at the supermarket on my way home. But it's not where I want to be. And again, we heard this particular thing this morning. I think IBM is going to get there before anybody else. But what I want is a research assistant. And I think it is possible to take the machine learning ideas and the ideas behind Siri and Cortana and to build something that can actually help me do my research. That I could go to bed at night and it knows that I'm interested in the following topics, and it goes out and it finds related research. It might even conduct some experiments. I might say, I want to try these computational analytics experiments, and then it goes off and it does that for me. And it could even maybe verify my math. All of this while I sleep. I like to sleep at night. Graduate students don't need it, but I do. And so I think that's important. So I think that's possible, and that's going to come. And I think we'll see a smart cloud service economy. We already talked about that in the panel. There's no reason to be building all the applications as monolithic things from scratch. Buy machine learning and other components for your app. Amazon, the Alexa voice services, and SkillKit API, the Siri APIs. We heard about the IBM Watson services this morning, the Microsoft machine learning tools, and as well as you're going to see some stuff soon about Scholar APIs. So these are, I think, things that are going to happen, and probably within the next couple of years. So that's it. Hello. Last slide. There it is. Anyway, thank you. I don't know if there's any time for questions. Anybody want to challenge me on anything? There we have a couple. Go ahead.
You mentioned moving the supercomputer into the cloud, as well as well. And something that people are not into, it seems to basic things, a lot of maybe the people cloud stuff is hardware agnostic. It's meant to be portable. It's meant to work regardless of the system. And I took a class on supercomputer programming for digital scientists, and they talked about Fortran, and they talked about knowing exactly how many cores you have. Do you think that the trend is going to be for more hardware-aware cloud or more hardware-independent kind of forms of computing?
Yes. No, I think we're going to see the hardware-aware cloud. In a sense, we already know how many cores we have, and then it'll be how many GPUs we have and what sort of FPGAs we have. And we'll have probably a choice of internal messaging networks. Should this thing be run on the standard cloud network, which is slow as molasses, or maybe some fast stuff. And then on the supercomputing side, I think they will see more demand from their users, and this is a very hard pill for supercomputing managers to swallow, for sort of interactive computation and data. I know the supercomputing centers are already dealing with how can we make data analysis easier, rather than just big batch computing jobs which spew out data. How can we take big computing jobs and do the analysis there?
My question is not about something you said. I'm going to ask you something else. What about the use of cloud computing in cyber-physical systems, like controlling machinery?
Yeah.
Controlling bridges, not controlling bridges, but looking at the structural health of bridges based on sensor data. Apparently, a Boeing 700 something in the land is maybe 100 terabytes of data. Right? How do we do solve the analysis in real time and some later on and that analysis and so on? What is the role of cloud computing here?
Yeah, I think that's a great topic. I sort of pictured when you said it, a big Boeing jet flying over the ocean. Before it lands, it dumps the data in the ocean. It got too much, and all those bits flying into the ocean. But I've been thinking about it in terms of self-driving cars, right? How much is the cloud going to be talking to my car when it's driving me, to a restaurant at night? The latency problem bothers me a lot there, and will it be able to help? In other words, this also relates to IoT and moving the intelligence down to the edge, and that was also discussed earlier this morning. And that as the sensors are coming in, the more data analysis you can do on the edge, and then keep the big data analysis going in the cloud, the main servers in the cloud in the background. But I think it's really important, but I worry about the issues of latency and bandwidth and congestion for life-critical services. We can't have the cloud be the back end of our smart cars, but they can play a role in pushing information down, such as terrible traffic jams ahead, or which they do now to our phones, or the other information about, the environment, the weather, things like that, or just the general driving conditions that I should be expecting. Whereas locally, the intelligence on my devices, my machine tools, or whatever they are, have to be controlled by local intelligence. And so finding the right sort of granularity of services and analysis that runs on the edge of the cloud that communicates with the bigger compute capabilities in the back end, the big data capabilities, I should say, is important. I think that's a great area of research.
Now that you see that the last year was learning was in talk, this is the tennis. Power and scale up to even change without extra effort. However, in this particular system, we can previously we talk about how much CPU we use, how much CPU blocks to use. That it's easy to use, but it's a kind of waste of using power. Sometimes this GPU or PC can and release hardware capacity, but GPU is very, very hard to tune.
Yeah, well, first of all, back when I worked for Microsoft, we told everybody you have an infinite computing on demand. And the truth is, you better demand and demand and demand, because you're not going to get infinite computing, and unless you've got very deep pockets. Customers with very deep pockets can get as much as they want, but in general, it's very hard to get a very large amount of resources in the cloud. Now, but more to your point, I see that specialized hardware, such as there was neuromorphic computing that was mentioned, that IBM is looking at, and other places are looking at that too, and it's a great research topic. And that's, a 32-core desk side box with a bunch of of NVIDIA processors could cost not that much, $50,000.
Especially if the cost managers.
Yeah, that's right. And so that's a great way to do a lot of science. I think really, we're in a trade-off period, and I think that's why I said I predict that more capability in terms of hardware will start moving to the cloud, and to the public cloud in particular, because the customers will demand it, because they, otherwise it's just a bunch of servers that just are good only at doing web indexes are not going to be the same thing as the servers I need to do deep, compute-intensive machine learning. So, we put together a big cluster at Microsoft Research. I probably shouldn't say this 5 years ago. And it was made from servers that we use for the search engine Bing. And as soon as we put this cluster together, it was for research purposes, we said, well, that's a lot of servers we've got. Let's put a big workload on it and see how good it is. And so we put the standard supercomputing benchmark, LinPack, on it. Blew out all the power supplies. And we had to rebuild the whole thing because those servers are just not that good compared to what you see in a major supercomputer. But they're getting better. That's the thing. Yeah. Right.
This is one question. The second question, if you can, just open discussion about the microservices. I think we're looking at the prediction of the future of the microservice. Are you going to think about additional web service, the service composition, the cloud, and
Okay, so there's two questions. One is the role of the hypervisor and the container stack. As we heard yesterday, the Google doesn't even use a hypervisor for their containers, and they run the containers they run an operating system on the hardware, and the container system basically reuses that one instance of the operating system. Now, in the case of public cloud, for security reasons, it's really important to maybe put the hypervisor there, and then you put in the number of virtual machines that you think that server is capable of. And so, for example, it was an 8-core, this is my own experience, use something with, say, 8 cores. And that'll be a server with 8 cores, or more modern server, 16 cores. And I might decide to put, 16 cores, I might put four virtual machines there. So that means each virtual machine gets 4 cores. Now, on each of those virtual machines, I could deploy maybe 20 containers. If I get above, actually more than 10, it depends upon the load each container needs. You may only have 1 container per VM. It really depends upon what that container is doing and how much memory it needs. So it's, again, as I said yesterday, the idea of the hypervisor gives you a level of security and from a separation point of view, security isolation, whereas the containers above it give you a way to do performance isolation within a single virtual machine. Now, the second part of the question, which was also good, but I can't remember, what was the second? Right. Microservices, right? Okay, so it's interesting. The first time I looked at the microservice stuff, I said, well, this isn't like, SOA, service-oriented architectures, right? What's the deal here? It's really about the decomposition into independently replaceable units. And it has become just the standard practice, whereas a lot of our service-oriented architecture stuff did not really solve certain problems. For example, continuous deployment and availability at scale out. Although the ideas are there, and I mean, I used to do Corbis stuff, and then I did all the WSDL things, and I thought that was really great, but it didn't really solve those problems. Whereas the lightness of these services, the microservices, which is kind of a funny name, but micro just emphasizes that they're small and stupid. They tend to be stateless. They tend to be replicated many times so that you have lots of scale. So I think there's a good future to it. It's very new technology. It's only been around sort of in the public sphere for about a year, but I think that Google and I know Microsoft and others have been doing this internally for longer than that, a couple of years. And that's their standard software deployment mechanisms now. To the extent that the rest of the community needs that capability, I think building an application in the cloud, if you need the scalability, if you need the resilience, this is the best way to do it. But then again, it's not been around that much. I've just only done one application that way myself. So having done one application, that doesn't make me the world's most profound speaker on the subject. Okay, well, thank you very much.